let me give you some useful shortcuts for taking definite integrals of even and odd functions under certain circumstances. Recall that an even function is one in which f of negative x is the same as f of x. The way that you can recognize an even function graphically is that it's symmetric across the y-axis. So let's say that we were integrating an even function on a symmetric interval, say from negative a to a. So let's say it was even, and we wanted to integrate that even function from negative a to a. Well, since the function is symmetric across the y-axis, the area over here on the left and the area over here on the right are exactly the same. So instead of going from negative a to a, what I could do is find the area just on the right side, which is the integral from 0 to a of that even function, and double my answer. So the integral from negative a to a is twice the integral from 0 to a when I'm integrating an even function. Let's look at an example of that. Let's do a specific example. Let's say that the function we're integrating is f of x equals x squared plus 4. The graph looks something like this. First of all, let's just verify that it's even. If I replace that x with a negative x, I get negative x squared plus 4. But then the square of negative x is exactly the same as the square of x. So f of negative x is the same as f of x, so it's indeed even. Now suppose I wanted the integral from negative 3 to 3 of x squared plus 4. Then I can make the work a little bit easier by changing this into twice the integral from 0 to 3 of x squared plus 4. Calculating the antiderivative. The antiderivative of x squared plus 4 is a third x cubed plus 4x, which I'll take from 0 to 3. And then I plug in the two endpoints and subtract. When I plug the 3 in, I have a third of 27, so 27 over 3, plus 4 times 3, which is 12, minus 2 times 0. 27 over 3 is 9, and 9 plus 12 is 21. So I get 42 is my answer. Notice it was kind of nice having 0 as my lower bound, because it was easy to plug in, and I happened to get 0 as my answer. Now let's look at what happens with odd functions. So the goal is to figure out what happens when I integrate an odd function over an interval which is symmetric across the origin. Algebraically, a function is considered odd if f of negative x is the opposite of f of x. Now graphically, what that means is that the function is symmetric about the origin. So what would happen if I integrated an odd function from negative a to a? Well, the area below the x-axis over here would exactly equal the area above the x-axis on the right side. But remember, areas below the x-axis are counted as negative, so when I add these two together, I'll get 0. So the integral from negative a to a of an odd function equals 0, and that can save a whole lot of work. So as an example of that, let's look at the integral from negative 5 to 5 of x over x squared plus 1 squared. Well, let's look at the function f and see whether that happens to be an odd function. So f of x is x over x squared plus 1 squared. So if I replace x with negative x, I get negative x over negative x squared plus 1 squared, which is negative x over, when I square this negative x, it gives me x squared. And notice that this function is the exact opposite of the function I started with. So this is the opposite of the original function. So the function x over x squared plus 1 squared is odd. So I know that this integral is 0 without having to do any calculus at all. Now that might seem magical to you, so let's actually carry out this integral using a u substitution and verify that the answer really is equal to 0. Let me make room for it up here. Let's look at the integral from negative 5 to 5 of x over x squared plus 1 squared. The u substitution we'll make is u equals x squared plus 1. So du is equal to 2x dx. Let's rearrange this so that I have the x with the dx. So I'm going to move this x over with the dx. I'll also take this x squared plus 1 squared and move it up to the numerator, using a negative 2 as my exponent. Now for my u substitution, I need 2x dx. So I'll multiply by 2 and divide by 2. And then I'm ready for my substitution. I have a 1/2 in front. The 2x dx became du. And this expression becomes u to the negative 2. Let's see what happens with the bounds. If x is equal to 5, then u is going to be 5 squared plus 1, which is 26. And if x equals negative 5, then u is negative 5 squared plus 1, which is also 26. Now I could keep going, but why would I? Remember that if both of your bounds are the same on a definite integral, then the answer is 0. I could keep going, but it would be really silly to do so. Notice I really am getting 0 for this integral.